We have derived the basic structure of the voltage control current source using a single MOS transistor. Now we will analyze it further and see exactly how it behaves. I'll assume that the load is a resistor that is connected to the drain. The input is applied to the gate. Of course, a real input source will also have a certain source resistance Rs. Okay, and we have a resistance R1 connected between the source terminal and ground. So what happens is, whatever drain current is there, or the output current, that goes through R1, and there is a voltage I0 R1 across R1, and that's also the source voltage of the MOS transistor. At the gate we have the input voltage Vi, because no current flows through the gate and there is no voltage drop across Rs. So the gate source voltage is Vi minus I0 R1. Okay. Now what is the actual value of I0? You can see that this current source is Gm times Vgs, or Gm times Vi minus I0 R1, and that itself is the output current. So to find the output current, all I have to do is to write this equation saying I0 equals Gm times Vi minus I0 R1 and solve for I0. Solving for I0, I get I0 equals Gm by 1 plus Gm R1 times the input voltage Vi. Now what is the relationship that we wanted to have? That was I0 equals Vi by R1. And you can easily see that this expression here reduces to that if Gm R1 is much more than 1. Okay. So if you choose Gm R1 to be much more than 1, the ratio of output current to input voltage in this circuit becomes independent of Gm. And independent of Gm means it is independent of temperature and so on, because the semiconductor characteristics Gm etc. are very dependent on temperature and also on other properties of the MOS transistor like the threshold voltage and so on. Whereas a resistor could potentially be accurately fixed. So it depends accurately on some resistance and it doesn't depend on the transistor at all, provided that the transistor provides a Gm which meets this condition. Okay. In other words, Gm much greater than G1. G1 is the transconductance we want to achieve. Okay. If I rewrite this expression, I0 is Vi times G1. So that's the transconductance we want to achieve. And if the transconductance of the MOS transistor is much more than the transconductance we want to achieve, then the resulting transconductance is only determined by G1, not by Gm of the transistor. Okay. So quite easy to analyze, and you can see this condition is very similar to what you got in case of the source follower. There Gm times RL had to be much greater than 1. And in general you will see that all negative feedback circuits behave in an ideal way if the transconductance, or in general some gain in the system, becomes much more than 1. Okay, those of you who are familiar with control systems know that if the loop gain is much more than 1, then the negative feedback behaves in an ideal way. So this Gm contributes to loop gain in the circuit, and if that is much greater than something, let's say G1, then you will have nearly ideal behavior. Okay. So now we have our circuit and we have also analyzed it. Okay. The exact expression for the transconductance I0 by Vi is Gm by 1 plus Gm R1, which can also be written as 1 by R1 divided by 1 plus 1 by Gm R1, and if Gm R1 is much more than 1, it is just 1 by R1. Okay. So that's the important parameter of the voltage control current source, the ratio between the output current and the input voltage. We would also like the input and output resistances to meet some constraints. So in this case, I won't spend much time on this. What is the input resistance looking into this? You can see that there is no current going into the gate. So whatever voltage you have, no current is going in. So clearly Ri is infinity. Similarly, you want to find out what the output resistance is. That means between this point and ground, wherever the load is connected. Okay. Let's do that. It's also quite easy to compute. I have set the input voltage to 0 and I have R1 here and GM VGS where this is VGS. Okay, and I want to find the output resistance looking that way, so I can connect a test voltage or a test current. Let me connect a test voltage for now. Now it's very easy to see that the gate is at 0 volts or ground. Okay, so this is at 0, and if you apply Kirchhoff's law here, what is this? Let me assume that the gate source voltage of the transistor is VGS, so this voltage is at minus VGS. So the current in R1 is VGS by R1 in that direction, and here we have GM times VGS. So applying Kirchhoff's current law here, we get VGS by R1 plus GM VGS equals 0. So the only solution is that VGS equals 0. Okay, so both this is at 0 volts and this is also at 0 volts. So this current source here is also 0, so it drops out of the picture. It becomes an open circuit. Okay, so this becomes an open circuit and this current is also 0. So because the current is 0 regardless of Vtest, R out is also infinity. Okay, what are the desired characteristics from a voltage controlled current source? Because it is voltage controlled, we would like Ra to be infinity, because then regardless of what kind of voltage source you use, right, that is however high the value of Rs is, if Ra is infinity, then there is no voltage drop across Rs and all of this Vi appears across the input of the circuit. Okay, so that's why in a voltage controlled device we would like Ra to be infinity. And it's a current source. A current source has an output resistance of infinity. Okay, our circuit has an output resistance of infinity and it is the same as what we would like in an ideal voltage controlled current source. But of course we have omitted something from the model of the MOS transistor, that is the parameter lambda corresponding to the channel length modulation. We assume that the incremental output conductance is 0, but it's really not 0. Okay, now in case of the common source amplifier and the common drain amplifier or the source follower, the output conductance, it changed the results a little bit, but it didn't make any qualitative changes. Whereas in this case you will see that the output resistance is infinity if you assume that there is no output conductance, but if the transistor has some output conductance, the output resistance will not be infinity of the voltage controlled current source. Okay, so it will make a qualitative difference to the result. We can analyze and see how much the output resistance is. Okay, so in this case it is important to model the output resistance of the MOS transistor. Again, I have my MOS transistor with VGS and GM VGS. I have the resistor R1 over there. Okay, and I need to have the output conductance of the MOS transistor GDS or the output resistance RDS. Now again, one of the mistakes frequently made by students is to connect it between the drain and ground. It should be connected between drain and source. Okay, in this case the source is not grounded. In case of the common source amplifier it is grounded and it appears between the output and ground, whereas in this case it does not. Now to find the output resistance, we can connect a voltage source and find the current, or connect a current source and find the voltage. In this particular case it turns out it's easier to connect a current source and find the voltage, and also we've been using the voltage source for far too long, so let's now connect a current source and find the voltage that develops across it. Okay, now the easy thing about using a current source is that when you have a number of series paths, the same current flows through all of them, and that can lead to some simplification. Okay. And we don't know how much current is flowing here and how much current is flowing there, but whatever goes into this has to come out here. So it should be very easy to see that the current here is simply equal to I test. Okay. Again, you can imagine that by writing down Kirchhoff's current law around that whole circuit. Okay, you know that Kirchhoff's current law is valid not only just at a node but any closed circuit. There could be some other components inside, because charge is conserved and there is no local accumulation of charge, right? So the total current going into a closed surface should be equal to 0. So the current here is equal to I test. That simplifies things. The voltage across it is R1 times I test. The voltage at the gate is 0, again because this RS is connected to ground and no current flows into the gate. So this VGS equals minus I test times R1. Okay, and this current source GM VGS will be minus GM R1 times I test. That's what is flowing downwards. So what is flowing upwards like this is GM R1 I test. Okay, and I test is flowing that way. Obviously the current through GDS will be GM R1 I test plus I test. Okay, so now we can write down the voltage drop V test in a straightforward way. It is equal to the voltage drop across RDS plus voltage drop across R1. The voltage drop across RDS is this current times RDS. So it is GM R1 RDS times I test plus RDS times I test. The voltage drop across R1 is I test times R1. We have already calculated that. Plus R1 times I test. This whole thing equals V test. And what is the output resistance? It's the ratio of V test to I test, and it is equal to GM RDS R1 plus RDS plus R1. Okay. So this is the output resistance of our voltage controlled current source. Okay. Now, what can you see from this expression? Is it going to be very large like we want from a current source, or small and it's not really useful as a current source? It's very easy to see that it's going to be quite large. Okay, because we have this number here, GM times RDS times R1. Now GM times RDS is the inherent gain of the MOS transistor. So this value of R1 is multiplied by the inherent gain of the MOS transistor, which is likely to be quite a large number. Another way to think about it is that GM times R1 has to be much more than 1. That is for our negative feedback circuit to work properly, right? So here we see that for this expression to approximate Vi by R1, GM times R1 has to be much more than 1. So this number RDS here is getting multiplied by a number much more than 1. So the output resistance is going to be much higher than what you see in a single transistor. The output resistance of just a single transistor is RDS. The output resistance here is GM-R1 times RDS. And there are some extra terms here, RDS plus R1, but you can see that this number here is much more than either this one or that one. In most reasonable cases, the transistor of course is assumed to be in saturation region. Okay. So this gives you a very high output resistance. Okay. So in summary, our voltage controlled current source. This is our implementation of the voltage controlled current source. Again, we have implemented the small signal incremental picture, then we'll combine this with some biasing arrangement. Okay. What do we have here? The ratio of output current to the input voltage is GM by 1 plus GM-R1, which reduces to 1 by R1 if GM-R1 is much more than 1. And in fact, this GM-R1 being much more than 1 is a criterion that you use to choose GM. Okay, if you have a certain value of R1, certain transconductance G1 that you want to realize, then you make GM much more than that transconductance G1. Okay, GM much more than G1, and Ri looking in here is in fact infinity because no current flows into the gate. Of course, when we add biasing arrangements to this, that may change. And the output resistance, which can be usefully modeled only with the output conductance of the MOS transistor or output resistance RDS, is given by GM RDS R1 plus RDS plus R1. The most dominant term is this. So what this says is R0 is much greater than RDS and it's also much greater than R1. Okay, so it does provide a very high output resistance, but just not infinity. Okay.